Is this visible for everyone? Okay. Yeah, so the idea of the tutorial was that I'll just show how things differ between GL and Vulkan. I thought at least half an hour would be needed for this. I'll see how quickly I can rush through this. So this is all the demo does. It's just a simple triangle demo and nothing fancy. So yeah, it's just a simple triangle with updating colors. So first of all, let's see how this thing would be done in OpenGL. So I assume that most of the guys were familiar with OpenGL. So you'd have basically you would have the window and the context creation, and then you'd set up the shaders and then the vertex array object and then your VBOs, and then your draw call would look something like this. Your render loop would look something like that. You clear the scene and then you update the scene, and then you basically just draw. So yeah, so question for the audience here. Okay, I should have hidden that. Yeah, so guys, so in OpenGL, do you know when this draw would be submitted? It was a question for the audience. Yeah. So GL, okay, I think I'll just answer that. So thing is, in OpenGL, you don't know when this draw would actually be submitted. So thing is, if you keep submitting these draw calls, the driver would have this internal memory where it caches all these draw calls and then submit it all at once. So a draw doesn't actually mean that it's submitted work for the draw. It just means that most driver implementations just have this temporary buffer where you would enqueue all the draw commands and then it would be submitted at one shot. So this is an optimization so that it doesn't need to keep submitting these. So this is something that's implicitly done in Vulkan. So there is no explicit behavior there. So first of all, as you can see, there's pretty much like 200 lines of code, and then this is including all the shaders and every setup code. So if you compare that with Vulkan, you already are seeing that that's almost about 1,500 lines. So don't get scared. This is mostly, pretty much all the code here could be reused, or it could be something that, you could add into a library and things would get better. So I won't be going into every function here. I mentioned some things were interesting, so I'll just go into those. So your flow would pretty much be something like this. You create a window and then you create instance. You set up your device. So all the device queue, all that stuff is done here. And then you create the swap chain. So I'll come back to this again. And then you create your command pool. So a lot of these code has already been shown, so I won't go into details. So this creates one command pool here. And then you create the descriptor set pool. So this is slightly interesting. Let me go to this. So yeah, in the descriptor set pool is where you show how many descriptors you have and then how the layout is actually defined. So this would be something like this. In my case, I have, let me just show the, so in my case, I have one UBO. That's pretty much about it. So I'll just need one descriptor set. Yeah, so this is how it looks. So I have just one descriptor set here, and for additional ones it's shown there. So all you do is set up this, and then you create the descriptor set pool for this. Okay, so there's another interesting thing in Vulkan wherein you actually execute some command buffers during the setup time. So here I create something called as a setup command buffer. So this is a temporary command buffer that's just used during the init time, and I'll just show where this thing gets used. So when you're setting up this depth and stencil attachments, the layout transition comes into picture. So layout transition was something I spoke about during my slides, and this is something needed so that the render pass could be actually used for, so that the image could be used in a render pass. So what you do in a depth stencil thing. So you have an image. Now you have an image. So you need to allocate memory. So similar to buffers, you need to allocate memory for the image, and then you create the image view for that. So I won't be describing every API here. So after you create the image and the allocate memory, and then you create the image view. Sorry, create the image view and then allocate memory. You bind it, and this is the interesting part. So this is a barrier used for this particular transition. So the original layout of this image was undefined, and now you need to actually use it in a render pass. And this is the layout you need that particular image to be in. So what we do for this? So that's where you need something called as a barrier, like I already explained. And in this case, we use something called as an image memory barrier. So what this memory barrier is used for is converting from this layout to this particular layout. I have some comments here. So this is how you issue a barrier. So the barrier has two stages. One is the source stage and the destination stage. So what the source stage says is that this is the last stage where the GPU wrote into a buffer, or this is the last stage where there is impact into that buffer. And then the destination stage is where it's the first stage where there is read into the buffer. So that's a brief explanation of what source and the destination mask is. And in this case, we just give it as top of pipe. So top of pipe is when the device actually starts processing these commands. So we want a layout to be transitioned before any of the commands are actually starting to execute. So we just give it at the top of pipe. You guys can stop if there are any questions. So because the code is pretty vast and I can't really explain every API. Yeah, so that setup, that would be some init, that setup is something that you do at the init time, and you use one dedicated temporary command buffer for that. And after you're done with that, you just flush the command buffer. So this is how you would flush the command buffer. So in this case, I just use a wait idle, but yeah, this is not something that you definitely need. Or if it's just something that you need at init time, it's still okay. So if you want to wait on the CPU, it's just something that you do like a one-time thing, then queue wait idle is still okay. But there are other ways to do it. So once the depth stencil is done, we go ahead, we create the pipeline cache, and we go to this allocate command buffers. And I have a question for you guys again. So here, as you can see, I have 3 draw command buffers. So any answers to this? So I'll give a hint. So there are 3 because we have 3 swap chain images. So it's a triple buffered rendering. So any ideas why we would need 3 command buffers? Okay, I'll just answer. So what? Where did I just go? Yeah, so that's another way in which you could avoid CPU waits. You can do this submissions in parallel. So that's the reason why you have. So, and this is a common pattern you see in Vulkan. You would have if you have n swap chain images or n buffers where you render into, you would have n of different resources. So that's a sorry. Yeah, you would have n of those resources generally, and that's a common paradigm you see in Vulkan. So where were we? Yeah, so allocate command buffers were done, and then so this is the actual command buffers you do for rendering. You record for rendering. So if you can see here, there's quite a lot of commands you record here. So you begin the command buffer. Again, you see that there are 3 command buffers that you're recording, 1 for each swap chain, and there is barriers again. So as I mentioned, the initial layout is undefined for any image, and for the render pass to write into an image, you need this color attachment, or in case of depth stencil, it was depth stencil attachment. So you need an image barrier here, image memory barrier here. So this just means that after all the commands are done, and then before the final, so bottom of pipe is just like literally the last thing. So all commands are done, and then like you have like bottom of pit, bottom of pipe, which is like the end of the pipeline. So after all commands are done, I want to transition into this color attachment so that the render pass could use it for future. And there's another interesting thing. So we need another command, another pipeline barrier to change it from this color attachment layout to this present source. So this present source is format you need for presenting the image into the display engine, which is the display. So the layout transitions are something that are, it's not probably very, it's not very intuitive, but you need this in every render loop. So you need to keep converting across these different image layouts. Yeah, and then you insert the barrier, you end the command buffer. So I think I missed one. So let me go. Sorry, that was a build present, not the render. Sorry, the render comes up next. Next we go into the render pass. Again, this is very interesting because render pass is a concept that never existed in GL. So as you can see here, it's so clean. The render pass just consists of the scene description wherein you say, I want these particular attachments, and you're pretty much just giving the entire scene description. So you can say that I have a color attachment and a depth attachment. In this case, it's a depth stencil. So I have color attachment and depth attachment, and in my render pass, I have one subpass. So there should be, one subpass. So what you're saying is I have two attachments in my render pass, and then I have one subpass. So as you can see, there is so much information you're giving to the driver, and the driver can do all sorts of optimizations. There was no such thing in GL, so you can actually use all this information in the driver for any optimizations you can think of, and then you just create the render pass. So if you were to do some multipass rendering, what you would have is you would have these as sorry, that is again irrelevant. Subpass. So you can create multiple subpasses and then create all these attachments. So you could do multipass rendering using this particular description, and it's very clean. Now we are done setting up the render pass. The frame buffer. So as I'd shown in my slides, a frame buffer is just a collection of attachments. And anyway, I wanted to just comment that in this particular case, we have one depth stencil attachment and three color attachments. So that's, three different image views for that. So that's just because that at any given subpass, there would be just, there would be one subpass active at any given point. So that's why you do that. So, and then you create 3 frame buffers, again, same thing. So you have 3 color attachments, which go into each of the frame buffers, but the same depth stencil attachment is shared by all of them. And the interesting thing is that pretty much the entire code is, you can share a lot of this code even if you go to a complicated app. So all of these setup would pretty much remain the same. So this is where you prepare your semaphores. There's not much interesting, so I won't be going at that. Prepare, what is this? Yeah, so here is where you would set up all your VBOs. So the staging buffer thing comes here. And yeah, I thought of asking a question. So anyway, the staging buffer was already explained. So you need that as a temporary buffer to copy your contents into your device local. So the staging buffer would be host visible, and they would be copied into your device local memory. Let me see if there's anything more interesting here. So we need to be done with this entire copy before we start rendering, right? So that's why we use another temporary command buffer here to just get done with it. And I just do a flush here so that before you start rendering, all these copies are done. So note that pretty much all this stuff was actually happening even in OpenGL. It's just that the driver was doing behind the scenes and you never noticed all this. So pretty much all the staging buffer and then there's implicit copying, all that used to happen even in OpenGL. It's just that the code looks pretty simple there. But all this was happening, and this was one of the things when you were asking, right? So where your predictability. So that's where. So in OpenGL you don't know, the driver is doing so much behind your scenes. Here you have so much explicit control over it. So this is another uniform buffer for the color that I use. So it's just a sample. So I've just hard coded it. So same thing again, and yeah. So I have another extra buffer for that one. So again, this is a pretty huge function. So this is where you create the descriptor set and the pipeline, descriptor set layout and the pipeline layout. So for the descriptor set layout, as I'd shown in those slides, you need to give what all you're using in the descriptor set. So after that, you would be creating your descriptor set layout. And so in this case, you say that you're using a uniform buffer, and then there's just one descriptor set. So yeah, that's pretty much about it. And then I just create the pipeline layout also in this function itself. And then I would allocate the descriptor, prepare pipeline. So this is probably the biggest function in this entire code. So this is where you define your entire pipeline state. So in case of compute, I think you would just have compute shader only. So in this case, obviously this is graphics, so you would need to define each of these things explicitly. So explicitly that even the rasterization state, everything you need to enable explicitly. So in this case, I don't want blending, but I still need to say that, yeah, I'm setting it to false.
So if you don't set it, it will fall back to
it's so most things in Vulkan, right? It's all like undefined. If you don't set it, driver can do whatever. If you want it, set it. So there is nothing that the specs as default value. This is not encouraged. So if you want it, be more explicit or be as explicit as possible. Dynamic states, I think Nilesh referred to it. This is something that would change dynamically, but you don't want a new pipeline state object for that. That's why you need a dynamic state. Yeah, coming to the shaders again. So this is where I think I showed the shaders already. So it was just a simple UBO with a simple color in it, and this was what I was setting as the vertex color there. And so you create the graphics pipeline. Yeah, this is the place where you build your render command, your render buffer, or what was it? Command buffer that does the rendering. So again, some more states set here, and you should have a render pass begin somewhere here. Yeah, begin render pass. So you begin the command buffer, and then you start recording. So again, the same thing. So you have n swap chains, so you have n command buffers, n draw command buffers, and you need to record these 3 times. So the best part is once you've done recording, you can just submit them without any cost. So this is all at init time. So note that we are still at init time. We haven't come to the draw calls yet. So this is just recording. So this is sort of like, think about it like you're recording a display list or something. So in GL, you don't, at least in modern GL, there is no way you can store all the commands in one place or something. So you record, and all commands that go into a command buffer have this CMD thing, so that it's very obvious to read. So all these actually actually translate into some command that would be read by the GPU. So you set some more things there, bind a descriptor, bind the pipeline. Finally we came to the draw call. So this is your GL draw. I think this is the first time we're seeing the draw call here.
1252 lines.
Yeah, and we're still at init time, so we haven't come to the draw yet. Again, more barriers. So in this case, you need to specify that the transition would be happening. So issue a pipeline barrier again, and you finally end the command buffer. So as you can see, the beauty of it is that you just do all this at one init time and just keep reusing everything. Finally, for the draw loop or the render loop. So let's see what happens in the draw function. And just to compare here, before I go into the draw of Vulkan, you can see how simple the thing is, right? but it's not very efficient. So your draws are actually submitting draws every time, and you might have some redundant checks happening every time. But now you'll see how neatly it's done in Vulkan. So acquire image is something that you have 3 images or n buffers you're rendering into. Before you can actually start rendering, you need to get this image, and before you can submit, you need to specify what all command buffers. Again, as the to-do mentions, that this is just so that the image barrier is complete. Of course, you can do it with a semaphore. I've just let it like that. Not a GL finish, but there's nothing equivalent in GL to wait on a queue, so I've just mentioned GL finish there. So once you have the image and you...
If I have fence there, I can get it, right?
Fence is also not needed. You need to use a semaphore, because fence is again a CPU wait, right? You should be using a semaphore. So you can just... This thing returns a semaphore, right? You can just get that and then do submissions. So actually there is an example of a semaphore here. So you see the wait semaphore here. So you should just be using semaphores wherever possible, and actually it should be possible everywhere. And then you finally submit the queue. So again, before you present, there should be a memory barrier. Queue submit. Actually, so anyway, I was just trying to find where the pipeline barrier. Anyway, so this is the draw call wherein it's more explicit. So you actually need to do this acquire every time before you do the submissions. And let's see what else is there left. Yeah, update scene. So in GL, you probably would do something like this, right? If you have a uniform, you would just say uniform 1F, or if you have a UBO there, you would still do GL map buffer and then update it. So let's see how it's done here. So yeah, you update the contents and then you map the UBO and then just do the final update. Again, I have another question here. So if anyone's interested, you can answer. So do you see any problem with this? So I have a single UBO and I try to update it. I try to map it. So is there any problem with this approach? Anyone? So let me see. I'll try to give the answer. Maybe you can try to come with a solution. So you have the same uniform buffer object being used everywhere, right? So the GPU could actually be using this and you're trying to update it. So even though it's host coherent, maybe the values could reflect, but then you're doing some sort of a place wherein the CPU and GPU are like, messily interacting with each other. So the solution is actually quite simple. You just do the same way how you do it for frame buffers or any resource that you create for every swap chain. You just have 3 of them. So when something else is being read, the other one would be updated. So map memory is still okay, but you just don't do it when it's being read anywhere. And the other interesting thing is Vulkan doesn't do any guarantee. So you say map memory, you get a pointer, and Vulkan doesn't really bother if your device is actually using it or not. It's all up to the application. So if you do this and then it causes some sort of corruption on the GPU because you updated values when you didn't want to, it's an app bug. So it's all responsibility of Vulkan to do it. And I think I said I would come back to one more function here, the create swap chain, right? So we are pretty much done rendering the the triangle now. And I'm just showing how the swap chain was created. So you specify all the width and everything, and then you create the swap chain somewhere here. Again, huge, whole lot of information to be sent. You create the swap chain, and you get these images called as swap chain images. So this would either be allocated by the windowing system or whoever does the allocation. So you get these images, and then you create image views out of them. So as you can see, you get the image count from the swap chain, get swap chain images, and then you would say in this case it returns 3, and then you have 3 image views created. So nothing really fancy there. So Actually, I would say the most complicated thing in Vulkan would probably be the synchronization part, wherein you need to do you need to use all these pipeline barriers, and the other part would be to how efficiently you can do multi-threading. So Vulkan does offer multi-threaded command buffer work creation, but it's not very obvious how you could do it in your app. So every app could probably do it in a different way. So that's really up to the app. Let me just summarize the main again. So just to do a simple triangle, you need to do so much, but even for a complex application, the flow is almost the same. Maybe what you would do is, when you're recording command buffers, maybe there are multiple threads generating the command buffers, and if it's an app that has multiple threaded command buffer generation dynamically, that'll probably go into your render loop as well. So the idea of this tutorial was to just give you an idea of how things would be set up in Vulkan and how it actually is so explicit and how it differs from GL. So hopefully we've given you some ideas of how things are different. So let me just briefly summarize. And create window, instance, setup device. I think Nilesh showed most of the codes there. I won't go there. So it's about creating the logical device, creating the queue, everything. I've just shoved it into one function. Create swap chain, command pool, descriptor pool. Yeah, this is some init setup, so you can have some things done there. Pipeline cache, allocate command buffers. Yeah, this is the present command buffers, and then you set up the render pass and the frame buffer. Prepare the semaphore. So prepare your VBOs, UBO. Yeah, that's pretty much about how to render a simple triangle. Any question? No? So I have a small demo. I mean, it's a quite fancy demo. So this is our internal demo, which pretty. I mean, it's actually there on GitHub. So this is a workstation related demo, and it shows how Vulkan could be used for. It shows all the benefits of Vulkan. So just to go to the slides again, what I'll be showing is this: how you can reduce CPU overhead and how you can scale your application with multiple threads. So it's a graphic card, and it might look simple, but it has tons of geometry in it. So it's got like, I think, 12,000 objects, and each of them have like lots of triangles inside them. So this usually the CAD the workstation requirements are like this. So that's why the demo looks like that. So if you see here, there are two bars. The green one represents the GPU time, and the blue one represents the CPU time. So our goal is to have this blue as small as possible, and the green as big as possible, so that the GPU is having more work. And let's just increase the number of copies. So let's say I have 5 of these. Why not? Now, as you can see, this thing it's V-synced. So I just switched off VSync now. Yeah. What is happening? 1 second. So this frame time should get affected if so there you go. As you can see, this blue is just like 22 milliseconds. If you can see here, it's about 23 something milliseconds, and this is about 13. So there's quite a lot of workload here. And if I switch the renderer to Vulkan, so there is one strategy. So the idea of this demo is that it's to show how you can do different strategies with Vulkan and compare that with GL. And there's actually a lot of GL options also, but I won't be going over them. So the first one in Vulkan is just you create one huge command buffer for the scene, and then you keep reusing them. So as you saw here, the blue line just vanished almost. So you have the GPU completely getting utilized, and there is no CPU work at all. And that's because in GL, what you would do is submit the draw calls every time, and there's so much state validation, all that stuff happening. But here, as you saw in the triangle demo, at init time you record all your command buffers and you just keep submitting them again. So there is no work you're doing at runtime, and that's why you have your CPU load completely reduced. And there is another thing here. So there are some multi-threaded strategies also. So this one, what it does is there is worker threads, and the worker thread could submit. That is the second strategy. But there is one strategy wherein worker thread generates all these command buffers, but the main thread does the submission. So if you can see that, as you can see, the blue line went up. So that wasn't expected, and the reason is we actually regenerate these command buffers on all threads every time. So like I said, this is just to show an example of how you would do it, and pretty much anyone who would want to do this multi-threaded command buffer generation would want them to be regenerated every frame. So if you just created it one shot, you probably wouldn't need multi-threads, right? So someone was asking why, if you can multi-thread. So if you have a static scene, and if you can encode all that into one command buffer, you don't need multi-threads. But if most games are very dynamic in nature, right? So if you have work that can be created in parallel and new work, that's when you need multi-threading. And this example exactly shows that. Now you have one worker thread. Now just see what happens if I make this as 2. Blue line just shot up. It just came down. So this is something that's not possible at all in GL. Of course, there is something called the shared context, which is not truly parallel. You can do some sort of a sharing, but it's all serialized in the driver. So this is something quite unique to Vulkan, and which is really good. Now you say 4
frames dropped, right, compared to GL when you had. It is now showing some.
No, that's the time. It's not FPS. It's time. The total time for the frame.
Oh.
FPS is not shown here. I mean, so the demo doesn't show FPS. So this is for showing how much GPU or CPU. That's the frame time in milliseconds.
It will be fast when you open.
Huh? Yeah. Okay, let me just show that. Make it like 100 copies or something. I haven't tried 100. Okay, let me see. Let me try 20. 20 is good. Let me go to GL. Let me actually go to the best strategy here, which is reuse command buffer, which is how much is it? 16 milliseconds now. Let me go to GL. It will just stop working. Yeah. So the blue bar hasn't even, now it updated. So it's very clear here that, and by the way, this is GL core. So this is raw GL. So there are some optimizations you could still do. So I shouldn't just say, switch to Vulkan if you have this. So there are strategies in GL. I won't show that now, but there are some proprietary extensions you could use to make your applications faster. But this is I won't be showing them now. So the idea is that you have so much reduced CPU workload in case of Vulkan. I think it's pretty obvious here, right? So let me make it worse. So there is a way in which you can do solid. So this just kills GL. So what this does is it has just two shaders, and for every draw, it just keeps switching. So I draw that. If you can see here, it has an edge. I don't know if it's, So there are edges for everything. So for the same geometry, I draw the solid, draw an edge, draw the solid, draw an edge. So you keep switching shaders, and performance is just gone. Now with Vulkan, obviously it is good. So there you would have 2 pipeline objects. Yeah. That's pretty much about this.
What's this on GitHub?
It's there. I can send you the link. So you can just search for CAD scene, Vulkan CAD scene. I can share the link with you. Let me just search. Right. Oh. Sorry. Oh. Okay. Sorry. Yeah, you can just search for Vulkan CAD scene demo or something, or you can just contact me. My email ID is there. I can just share it with you. But yeah, it's there online. So there's another multi-threaded application called Fish demo. You could probably check that, but this I felt was more nice. I mean, I personally like this better. So there is a whole lot of other options also in this, but I don't think I can be able to show that now. But yeah, that's hopefully we've convinced that Vulkan is something exciting, and all you guys might think about it. Although the number of lines is more. But trust me, I think when I started also personally, I was like, why do you need all this? But as you keep using it, you learn that there's so much power in it. So I always was a GL guy. So and I used to like GL because you can get your things done. But if you really want to get your things done, and especially in production and with highest performance, I think Vulkan's really good. So yeah, that's it.